get some sound there?
There you go.
So, I'm on. Okay, great. Real pleasure to talk to you all today. Appreciate you coming out. I do apologize. The title of my talk and the subject of my talk is not what's in the program. It's a total bait and switch. You got suckered in here. And it's a result of my talk, my original intended talk, overlapping like 90% in content with the talk that's going to be tomorrow. And so I decided to switch gears so that it wouldn't be total redundancy. It'd give you a reason to come back and hear Dr. Sertich's talk, who's back in the back of the room there. And he'll do a great job of talking about all the new dinosaurs that we found in Grand Staircase. If you're upset about that, you can leave a bad review on me on Yelp or something, and I'll remember that in the future. But what I want to talk about today is a little extra context, you know, about all these wonderful dinosaur finds that we've been making in southern Utah, because this is the place, to paraphrase or to quote somebody famous, for dinosaurs. I don't know if you've gotten that idea over the course of the last few lectures, but Utah really is a unique place on all the planet to be studying dinosaurs. And you can just kind of take for granted when they show all this artwork with all these wonderful dinosaurs in it that, oh, that just happens by magic, kind of like Ken's fossilization and Mickey. It all happens by magic. The paleo artists and the paleontologists just get some sort of metaphysical vision of what the environment was like, and they throw all these new animals in there. But that's not how it happens. And I wanted to talk a little bit today about the deductive process that we go through to try to decipher an environment. And I'm going to single out one particular formation, the Kaparowitz Formation, which has yielded the most new dinosaur species in southern Utah. We've named 12 now, 12 new dinosaur species in the last 10 or so years. Actually, our first one was in 2005, so 12 years. And that's keeping pace with just about anywhere else in the world right now. We're also online to name several this year. So the Kaparowitz Formation is exposed within Grand Staircase in the Kaparowitz Plateau, which is a large landform sandwiched between the Grand Staircase part of the monument off to the left of the map here. This is a Google Earth image. And then the Circle Cliffs, which is in the upper right-hand corner. And it's sort of a triangular gray wedge that comes to a point at the northern end, at the top. Can you make that out? Sort of. Oh, do we have a laser pointer? I know there's probably one up here on the... That's not it. I just got myself in deep doo-doo. There it is. Okay, so there is the Kaparowitz right there. Right? So I'm just going to run through the formations real quick. I don't have a lot of time to digress on the geology, but it's about 7,500 vertical feet of rock layers with vertebrate fossils in virtually all of it. Spanning about a 27 million year period of time, starting at about the time that Dr. Zano's talk was talking about, back about 100 million years ago, all the way up to just before the Great Extinction, 66 million years ago. So we have the Natarita and Tropic formations on the bottom, which record the advance of a seaway. So the Tropic formation at the bottom there is largely marine deposits with marine fossils. We do get dinosaurs, but they were really lost. Then we get the Straight Cliffs Formation, coastal environments. Finally, the Wawweep, about 1,600 feet of non-marine sediments that also have dinosaur bones in them. Lythronax, Diabloceratops, all that came out of there. And at the top of this stack, the Kaparowitz Formation, which I'll be focusing on. And that's about 865 meters, about half a mile thick, and it spans a little over 2 million years of geologic time near the end of the Cretaceous. There's a typical outcrop along Highway 12 on your way to Escalante from Henryville or over near Bryce Canyon. You can see the beautiful pink cliffs of the Claron Formation over there at Powell Point. And the KPG boundary, the extinction event, is basically mirrored in the color change from gray to pink. There's another outcrop of the Kaparowitz Formation in a little more remote setting. but just a wonderful place to find bones. They're everywhere. We've excavated lots of skeletons. Every year we find new sites, individuals, and bone beds of multiple individuals, and lots of other animals as well. Turtles, fish, crocodiles, mammals, flying reptiles, things like that. So this is one particular ceratopsid site that's being excavated. And from those sites, we've named an amazing menagerie of new animals. Just here, we have Gripposaurus monumentensis in the upper left. We have Cosmoceratops, the horniest dinosaur ever found, in the upper right. We have Teratophonius down in the lower left. And then on the bottom right, of course, the greatest dinosaur ever named. But how do we come up with environmental context for all these animals? You know, there's lots of dinosaurs, similar dinosaurs, in fact, being found in Asia. And those are interpreted as have been living in sort of savanna to semi-arid environments. Were the Caparowits animals, which are similar biologically, living under similar environmental conditions? And if so, how can we deduce that? So this is an artist's reconstruction of Nasutoceratops and a herd of Parasaurolophus living in a really wet, sort of swampy environment in the Caparowits. How did we come to this? How do we make the deductions that this, in fact, was really wet and tropical? Well, let's start with the rocks themselves. The rocks have the fingerprints all over them of very specific environmental parameters. So let's look at the cliff face up here in slightly more detail. And you'll notice that the typical sequence of Caparowits rock here is alternating mudstone, which is very fine-grained particles of clay, very small grains of silt and clay-sized particles of quartz, interleaved with coarser-grained beds of sand. And these sand beds indicate where there was current flowing, and the overlying fine-grained particles indicate periods in which there was no current flowing or very sluggish, slow currents. So these are alternating indicators of higher energy water environments with slack water. All right? And it turns out that the indicators there tell us that this represents an event. This sand bed is actually the genesis of a lake system, caused by the breach of a levee of a nearby river system that would breach and flood out into the surrounding flat floodplain or lower areas adjacent to the river with a sheet of sand in the initial flooding event that was high energy, and then the lake forms, a flood basin lake, and the slack water allows mud to accumulate over the next few decades or perhaps even centuries. And then as you look at this sequence, the sand gets thicker and comes faster, and there's less mud, meaning the frequency of the flooding events is going up. And ultimately, as rivers meander, like they're apt to do, the environment changes from near the river to actually in the river. This thick sand bed at the top is river channel deposit. These are sandbars from within the channel itself. So you're seeing a migration of a river into an area. Okay? Well, rivers can occur in a variety of settings. This is a river feeding the Amazon, a tributary of the Amazon down in South America under tropical settings. And this is a river in Botswana. So rivers, perennial rivers, can exist in a variety of environments. I mean, the Colorado is a perfect example of a river that exists in a fairly arid setting. So what kinds of environments existed outside of this river, and how can we deduce those, even though now I've eliminated all sorts of environments other than those that are characterized by the comings and goings of rivers? Well, this is a cross-section of the lake sediments that were deposited, and later it dried out, and a tree rooted into the muds after the lake dried out. So this is actually exposed root system of a buried tree stump. And this nodular ledge down here is calcium carbonate. It's lime, or basically caliche, that formed near the top of the water table in this ancient environment. So it's not very far from the surface of the land where this tree was rooted down to the water table, right? That's an important thing to remember as we're trying to decipher the ancient environments. Because all of the rocks of the Kaparowitz are actually shades of blue, greens, and gray. And that's a very important environmental indicator. So blue, greens, and grays, I sometimes refer to the Kaparowitz as 50 shades of gray because it's nothing but gray. The tourists don't generally flock to this place because of the colors, but it means there's bone. And the blue, greens, and grays mean that there is a high water table. Because, as we saw in the last slide, they reinforce that notion because oxygen is not able to get down into the soil and rust the various iron minerals that are down in there and turn them shades of what? Brown, orange, and red, which is what happens when iron rusts in a soil. You create red-colored soils. So these irons are actually reduced because they're constantly submerged underwater and they're being reduced by microbes that like to digest iron and keep it in an unoxidized state. They're also slightly alkaline, which is sort of a sidebar on the whole topic. But alkalinity is great for preserving bones. So that just turns out to be a bonus for why we have all the bones. Lots of alkalinity. Which, as it turns out, is kind of a paradox because generally you don't get high alkaline soils until you get into sort of desert environments. So maybe that's a mixed signal. And we have to wrestle with that concept. But overall, the colors of the soils are indicating it's fairly wet with high water tables. And there's not much organic material being preserved. So they stay aerobic or aerated long enough to digest all the carbon in there. We're not getting coals like you would in a swamp. Okay, now these sediments, these muds in these lakes start out as lake deposits. And here I've excavated the beautifully preserved pearly shell of a fully articulated clam with a couple of snails off to the left, which are the primary condition of the muds that we find in these lakes that these dinosaurs were cavorting around. And this clam right here is at least 50 or 60 years old. I mean, it takes decades for these big freshwater mussels to get this big. So these lakes are hanging around for a little while. These aren't ephemeral playa lakes that come and go in a season or 2 or 5. These lakes persist for decades. And then eventually they dry out. They get soiled over, and then the trees penetrate down in, and this shell starts to go away. Okay, so now I've established that at least it's waterborne sediment that is deposited into an area with high water tables. Is it cool? Is it hot? Is it really rainy, or is it really dry and the water tables are just high, like you can see in places in the Yucatan? Well, so we want to look at the climate, which is an average of the weather. What's the average rainfall? What's the average temperature? And that'll say a lot about these ancient environments. Well, the first thing we can do is try to get an idea of the mean annual temperature. That'll tell us whether it's Arctic, whether it's temperate, warm temperate, subtropical, or tropical in nature. And it turns out one of the best ways to do this is to measure the toothiness of leaves. So if you look at a modern magnolia leaf, which is more or less a warm temperate to tropical sort of plant, its leaf margin is very, very smooth. When you look at a modern elm, it's very toothy. And botanists think this has to do with, in cooler climates, plants like to push out a lot of fluid and stuff in front of them when the warm season starts so they can get an edge on photosynthesis over their tropical cousins. So this is a cool climate adaptation in leaves, this toothiness. And it turns out if you count the number of smooth margins and compare it in a ratio to the number of toothy margins, you should get some rough idea of the ancient temperature. You can also go in and analyze carbonates calcium carbonates, and also apatite, the mineral in bone, and look at the isotopes, stable isotopes of oxygen in particular, and get a sort of proxy for the temperature, because as temperatures go up, you get enriched for heavier forms of oxygen. So I'm going to just let the cat out of the bag and give you the results. Okay. So 21 to 23 degrees for the plants, and that's based on the margin. So there's a little bit of toothiness on that one. And then the isotopes came in at about 20 degrees. And if the shade from trees is covering the soil, you can actually have to add another 6 degrees to the isotope results in the soil to come up with the temperature based on some research I've done. And you can ignore that. So possibly as high as 26 degrees using the isotopes and analyzing that. Now, bone gave us an anomalous signature kind of low compared to the other two forms for temperature. So, bone was coming in right here. So we're probably about 40 plus degrees latitude, and bone's coming in well below the plants, which are telling us 20. They're down about 16 degrees. Now, what does that mean in terms of today's climates? Where does that put us in a temperature context for today? Well, the 20-degree mark is basically the boundary between subtropical and warm temperate. It's around the northern limit of palm trees and gators. Okay, let's look at rainfall. So we now know it was warm, sort of on the edge of tropical. You can also tell rainfall, and this is the best method, from the margins or from size of leaves. So the more large leaves you have in the assemblage, the more rainfall you assume you had. So you analyze the size ratios of all the different leaves and come up with an estimate on precipitation. Turns out, based on all of the leaves analyzed from 55 different species of leafy plants, that you have about 1.8 meters of rain a year. That's it's almost 6 feet of rain a year. We get about 11, 12 inches now. So that's a lot wetter back in the Cretaceous. And it's very comparable to the rainfall conditions we see on the modern Gulf Coast down around southern Mississippi, southern Alabama, northern Florida, East Texas. Just looking at the plants real quick, we have a variety of mosses and horsetails that are fossils, a lot of ferns that appear as fossils, a lot of conifers, all of which today require water, and some of which are actually tropical in nature. We don't see the kind of cold weather conifers or arid conifers that you might see that are even growing there today, like junipers. And maybe most importantly, palm trees. Lots of fossil palm trees in the Caparotes. There's ginger, fossil gingers, which we associate with the tropics, fossil tropical laurels, and climbing vines of different sorts. The fossil animals also would suggest, a wet environment. So this is a sample of some of the animals that are being found alongside of their dinosaur compadres, toads and frogs, salamanders, and these sort of siren-like animals, soft-shelled turtles, actually about 16 different species of turtles, but only one tortoise, so most of them liked water, caimans, all sorts of gators, and lots and lots of fish fossils. And these are really prominent, the fossils of these large alligator gars. Now, we don't find those outside of really large lake systems in the southeast U.S. today. They also are all over the tropics. And really, really big gators. These guys are going to need big, big lakes to hang out in, right? Or rivers. And people have been talking about the tyrannosaurs as being the biggest predators in the ecosystems. I'm sorry, but in the Caparotes ecosystem, the tyrannosaurs did not rule the roost. These large gators were certainly the most fearsome carnivores in the ecosystem. So just in summary here, today the northern limit of crocodiles and palms occurs right here in the southern margin of the U.S. And we run out of palm fossils and gator fossils basically somewhere in central Alberta, Canada in the Cretaceous. And yet the continents within the ballpark are riding at about the same latitude as they were back then. So we have an extension of these tropical conditions northwards up into Canada. And the complexities of why that is are beyond the scope of my talk, but there certainly was a lot more carbon dioxide in the atmosphere, and we had a lot of warm water being pumped up from the tropics into the central part of the continent through the Western Interior Seaway. So in summary, we were looking at basically tropical to subtropical conditions and very high rainfall, but not rainforest conditions. So it would dry out occasionally, and we have found sites with charcoal, and they would get fires, periodic droughts. And you're well above the ancient Cretaceous limit for these palms and gators. So you're going to be down into probably full tropical conditions down here. A little closer look at the region in this bight of the seaway. Lots of rain coming in, and very similar to the Gulf Coast today. So it's not a desert. Our best analogies are the Pantanal, since you're right up against the mountains of the ancient severe fold and thrust belt, which is the upper reaches of the Amazonian basin, right where it's lapping up against the Andes. Very wet, very lush, tropical, and full of caimans and gators, well, not gators, caimans, and all sorts of similar sorts of animals. So there's Utah 75 million years ago. Very different from what it was like 40 million years earlier, and not even 10 million years later. This was a unique period where it was really wet and warm. So there's another Pantanal shot. And I can imagine a Deinosuchus hanging out in one of these lakes. So that's how we come up with these paintings. These aren't just the wave of a magic wand. We actually do a lot of research to get the plants, the rainfall, the temperatures, the basic climes to be able to put these animals in. We don't just randomly put dinosaurs into a painting on some sort of generic jungle. I mean, every plant that's in this painting has been found as a fossil in the Kaparowitz. And it takes a lot of work. It took years of research for us to be able to paint this picture in this much detail to give you an idea of what it actually looked like. Okay, thank you very much. I do want to credit everybody here and leave you with the take-home that dinosaurs, as Dr. Zano said earlier, are not extinct. Do I have time for a question? Okay, yeah, I have time for a couple of questions if anybody wants to hit me up. No, I would doubt it, because it's been a lot colder in the near geologic past during the heights of the glaciers, 100,000 years ago, and that probably would have pushed those palms out of the environment. They've probably come up since then, would be my guess. Yeah. Mm-hmm. Yeah, so I don't see a direct succession from the Cretaceous for these palm trees all the way to today. Yeah, it is. What's even crazier is we had a gator living on the Arizona Strip. Somebody put one into, it was introduced, he didn't get in there by himself, but somebody put one in Pacoon Springs, which is a thermal spring on the Arizona Strip there at 5,000 feet above sea level. And because it was a warm spring, he was able to survive in there for over a decade. So, gators apparently were there then and can still live there now under the right conditions. Yeah.
Basically,
Well, that's a great question. How do we know whether a dinosaur was in a particular location that we made a painting for? Yeah, okay, well, the painting is just sort of a synopsis. It's just a generalization of what we find in a formation through an entire area. So we'll be looking through hundreds of square miles of rocks, and everything we find in all these rocks gets sort of summed up in that painting. So it's like a Cliff Notes or a Reader's Digest version of everything we found. Does that make sense?
yes.
Okay. Okay, I guess we're done. All right, thank you very much.